SpaceX's colossal Starship hurtling through the super-thin Martian atmosphere and trying to slow enough to flip over and touch down successfully with the available propellant. It is a good question and one I've been curious about for quite some time. I think you are going to love this one. I guess a quick explanation to why I've made this video in the first place. A few months ago, I spotted Sid here on Twitter talking about landing a Starship on Mars. In that tweet she mentioned that Mars has a rather unfortunate atmosphere, not enough to slow you down much, but enough to burn up the hull. I specifically queried the header tanks and propellant needed to land on Mars, to which Sid replied with a cheeky, "Can't explain how much I want to answer this. LOL. Obviously SpaceX can't provide information to the public without approval, but it certainly added some motivation to talk about this a lot more in a video. So I'm sure many of you are already thinking that I might be jumping the gun talking about the distant milestones for SpaceX's Starship. Orbital test flights, re-entry testing, refilling missions, and all that sort of thing need to come first. After all, that is indeed all required to make Starship viable for any long-distance mission. Given that Elon Musk is literally trying to disrupt the entire space industry with the first colossal fully reusable launch system, it is easy to miss the complexity still outstanding that is required for that aspirational goal of putting boots on the Martian surface. I've had a bunch of you over the last 6 months or so asking if the current Starship design and layout is about the same as what will be landing on Mars. The obvious requirement of the vehicle needing legs to land I'll exclude for now, but one thing has bugged me. Can this vehicle with only propellant in these header tanks scream into the Mars atmosphere, flip over using its engines as we've seen with these crazy flights in 2021, and then touch down? Well, you know, we've seen it work here, right? I mean, yes, these were just prototypes, and they blew up a bunch of them in full-on crazy SpaceX style, but yes, this sci-fi looking future all of a sudden began looking real plausible for distant missions where we are colonizing Mars. Regardless of various opinions out there, this is a super gutsy engineering achievement that got a lot of attention. Sure, timelines tend to be well beyond realism, but, well, you know, that is the story about the majority of any space project, isn't it? How many can you list that were estimated within a certain time frame and actually met that target? We choose to go to the moon in this decade, yep. This one comes to mind in the crazy space race that was the Apollo program. Let me know if you can think of any more below. Okay, so what are these for? Oh gosh, he's going to drill into stuff we already know, isn't he? I know what a header tank is for Marcus, get on with it. This is fair. It is hard of course to have a video like this that can stand on its own without at least defining a few things. Just quickly, this is Starship's main tanks for launch and interplanetary burns. These little dinky tanks in the nose here remain filled with liquid oxygen and liquid methane, and they will remain full until the landing burn. In previous designs, only the liquid oxygen was in the nose, but the new design dictates the liquid methane has now been moved up here as well. This is the only propellant available at the time of landing as far as we know. After all, for long-duration missions, such as to Mars, it is much more efficient to keep the small header tanks at the correct temperature than it is for the main tank. If you want more information on the tanks and how they are pressurized, this video will give you a bit more background information on all that. I'm not certain if there would be a great deal of energy requirements to actively cool the propellant on the journey. With the cosmic background temperature only being 3 Kelvin above absolute zero, comparatively, the tanks only require around 90 Kelvin above absolute zero. So it could be possible to just passively radiate off excess heat assuming the header tanks are well insulated. The bulk of the heat of course would likely come from the engine bay being pointed towards the sun. While this is quite speculative, keeping things cool in the vacuum of space may be easier than one might think. Now, there have been a number of people trying to estimate the sizes of these header tanks, and we don't have any official numbers anywhere on this. Apart from observations with the old one Malawian Kwacha eyeball and images spotted at various times. From what everyone has been able to sleuth out, the tanks hold somewhere between 16 and 19 cubic meters of propellant each, with the methane tank being slightly smaller. Now technically the feed lines should also be included in this total volume, but it's very hard to make any estimates on the volume within these on that for future ships. I even wonder if these lines will be filled on a long trip to Mars anyway. You need to keep the propellant cool just below their boiling point at all times. That is -183 degrees Celsius for the oxygen and -161 degrees Celsius for the methane. Only 22 degrees apart, and it is a real juggling act to keep the entire volume contained for months on end. When the methane absorbs heat and starts turning into gas, you need to quickly chill it back down, or vent it. Venting it means it is lost, so you don't want to do that. Zero boil-off is something that is still to be designed at this